Next slide. Planet atmospheres slow down the rate that heat escapes from a planet's surface or interior, as well as distribute heat over a planet's surface. Because there is a temperature difference between the surface or interior of a planet and space, heat energy will flow from the warmer surface to the cold space, according to the second law of thermodynamics, a universal law of nature. There are three ways gases can transfer energy. Number one, radiation. Photons, energy packets, leak outward by scattering off gas particles. Nature prefers this way. Number two, conduction. Fast-moving atoms collide with other atoms, imparting some of their motion to them. This is used by metals like copper or aluminum to transfer heat, for example, from your stove element to the food. But it is not used by a gas, since the gas molecules are so far apart from one another. The process of conduction is too inefficient in a gas to worry about. This is why you can stick your hand into your oven while something is baking and not immediately burn your hand if it does not touch anything, especially the metal sides and rack. Number three is convection. Big pieces of the atmosphere cycle between cold regions and warm regions. Hot air below expands and its density decreases, so it rises. Cooler, denser air falls and displaces the hot air. As a hot bubble rises, it cools by giving up its heat energy to the cool surroundings. The gas will then fall and heat up when it comes into contact with the warm surface or interior. It is a sort of energy conveyor belt motion of gas. Nature will use convection only if there is a large change in temperature over a small distance. Such conditions are found in planet atmospheres. Compared to the size of a planet, atmospheres are very thin, and also in the interiors of stars. Notice in the picture, I purposely drew one of the arrows going sideways. In addition to transporting energy outward to space, convection also distributes heat across the planet, from the warm, day-lit equatorial regions to the cooler latitudes closer to the poles, and to the night side of the planet. The warm air at the equatorial regions rises, and the cooler air from other parts of the planet flows across the surface toward the equator to replace the rising air. All of the winds in a planet's atmosphere are due to convective processes. If the planet is rotating quickly enough, the motion of the air can be deflected sideways by the Coriolis effect. If a pocket of air from the pole moves towards the equator without changing direction, the Earth will rotate beneath it. The packet of air has a sideways motion equal to the rotation speed at the pole, but the parts of the Earth's surface closer to the equator have a greater rotational speed because they are farther from the rotation axis. To an observer on the ground, the path appears deflected to the west. The Coriolis effect on a spherical body is actually a bit more complicated than just the east or west deflection I describe here, but for this course it is sufficient to say that objects will be deflected to the right in the northern hemisphere and to the left in the southern hemisphere, even for objects traveling due east or due west. The Coriolis deflections produce the spiral patterns of cyclonic storms, winds spiraling inward counterclockwise in the northern hemisphere, and clockwise in the southern hemisphere, and airflow away from high-pressure regions. Winds rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. The rapid rotation of a planet will also complicate the convective flow of energy from the warm equator to the cool poles. On a planet with little or no rotation, Venus, for example, the air circulation is very simple. Warm air rises along the equator, flows at high altitudes towards the poles, and near the surface returns to the equator. On a planet with rapid rotation, Earth or the Jovian planets, for example, the surface winds from the poles are deflected into large-scale eddies with belts of wind and calm. That's why on Earth the prevailing winds will usually be in one direction for a range of latitudes, and in the opposite direction for a different range of latitudes, and latitude bands where it can be calm for many days. At high altitudes, narrow bands of high-speed winds called jet streams are formed, and they play an important role on the surface weather. Land masses sticking up into the airflow disrupt the spiraling circulation and provide a place for storms to expend their energy. The rapidly rotating Jovian planets have much greater Coriolis effects. Jupiter is 11 times the diameter of Earth, and its rotation period is less than 10 hours. The powerful narrow jet streams deflect the clouds into belts moving parallel to the planet equators. The winds in a belt move in the opposite direction of the belt next to it. Clouds are usually made from minor ingredients in a planet's atmosphere. For example, water vapor makes up only 1% of Earth's atmosphere, and water droplets make up the clouds. Why do we care about clouds? Clouds can block input energy from the sun, a cooling effect, and trap energy from the surface, a heating effect. The slide shows the water cycle, or the hydrological cycle, on Earth. The water cycle picture and the picture below it show the effect of mountains. Mountains can disrupt or change the circulation of the atmosphere. They also create a rain shadow effect. As air rises, it cools off and the water, or carbon dioxide on Mars, condenses to make clouds and precipitation. The other side of the mountains, with respect to the prevailing winds, doesn't get the rain, so it is more like a desert. I copied a section of a NOAA memo about the Bakersfield climate below the rain shadow picture. The Diablo Range and the Tehachapi Mountains keep us dry. Other famous rain shadows are formed by the Cascade Range that separate western Washington and Oregon from their eastern halves. Oceans also affect atmospheric circulation by transporting heat energy and water, healing or cooling the land and air. For example, the narrow California current moving southward from Alaska makes the coastal waters cooler than the coastal areas of the eastern United States at the same latitudes. The eastern seaboard has the Gulf Stream ribbon of warm water from the Gulf making it warm, and continues up and across to Europe, making its climate comfortable.